Hello everyone. I would like to continue with the lesson on rate of change. Before I get started with this example, I would like to remind everyone of the formulas that I have indicated here for everyone regarding rate of change. So rate of change has a lot to do with differentiation, and you take derivative of a function in terms of time. Okay, so we have three formulas to work with. We have instantaneous current as a derivative of charge with respect to time. And you also have instantaneous current as the capacitor multiplied by derivative of voltage with respect to time. And we have instantaneous voltage as the derivative of current with respect to time multiplied by the values of this inductor. Okay, so for our example number 1, we are working with the instantaneous current. So very simple, which is the chart in terms of time. And I give a reminder for everyone the terminologies of what it means by all of the formulas. So for this example number 2, you are given V, okay, as a function of time. So you also given the capacitor and asking for the current. So we know that we need to use these formulas right here. Okay, so this is a formula that we need to use. Okay, and for example number 3, we are going to work with finding the voltage across an inductor. So in this case, you know that the formulas you should be using is V equal to the value of the inductor multiplied by derivative of current with respect to time. Okay, so this is the formula that we are going to use, even though they don't say instantaneous voltage, but we know that at that moment of time, we are having certain value for the voltage. Okay, so before I continue on, I kind of give everyone a reminder here. Be mindful of your significant digits, and we have to round to the required significant digits, even though the question doesn't say or indicate how many significant digits that we have to round to, but we have to know that if all the variables here, okay, having a coefficient with 3 significant digits, then we need to make sure that our answer is in 3 significant digits. And put your calculator in engineering mode, okay, in engineering notation. And in order for you to have as a number as precise as possible for the significant digits, then you need to work with as many decimal places as possible. Just keep those decimal places in your calculator, and to maintain the precision when you round to certain significant digits. Alright, so I am given the equation of I with respect to t. So I will rewrite this equation in terms of the exponent so that I can prepare myself for the next step that I differentiate this in terms of time. So I have t to the exponent 3, that's already there, minus 90 times t to the exponent 2/3. Okay, so the next step is I will find derivative of I with respect to time. So I will have 12.5 times 3 multiplied by t squared, 90 times 2/3 multiplied by t, 2/3 subtract 1, I should have negative 1/3. Okay, so at this point, I want to simplify this. There's a few ways that you can do this to get to the solution. You can leave all of this here. However, at this point, what I'm going to do is I want to have a different approach in case that you want to work with this, instead of leave all your number here and put them all into your calculator all at once. But what I do in this case, I'm giving you this simplified differential equation for the instantaneous current with respect to time. So right here I should have t to the negative 1/3. Okay, so I simplify the equation to this, and then the next step is I'm going to apply my formulas. di over dt. So in this case it will be equal to, but I better say that I evaluate this one at the time t equal to 12.5. Okay, so 12.5 seconds. So this equal to, I will write 7.5 milli, and in the bracket I have 37.5 times 12.5 square, subtract 60 times 12.5, all of this raised to the exponent negative 1/3. Okay, close this bracket. Okay, so what I'm going to give you is this number. So 12.5 raised to the exponent negative 1/3. So I would like you to take out your calculator and then key into your calculator like this. Okay, so I will write a step down for everyone. I will put in here my 12.5. Okay, so I'm doing this at the same time, using my calculator at the same time while I'm telling everyone. So 12.5, and then I put the hat. Okay, that means showing that to the exponent, and I put a bracket, and I put a negative sign. Don't forget that you should have a negative sign. Don't mistaken the negative sign with the subtraction. So the negative 1, and I put divided by 3. Okay, so 1 divided by 3, close the bracket. Okay, and then I press equal sign, and then equal sign, I should have this number 0.430886938. Alright, so this is all the number that I have here. So to show you how to work with the calculator raised to this exponent, as I mentioned in previous example, I thought I demonstrate the step so that you can make sure that you get this number correct. Alright, so don't forget bad math. So V will be equal to 7.5 milli, and all of this number that I have in here, so these number, okay, so this number will become 5833.521784. Okay, I multiply this with this, putting my calculator in engineering notation, I end up with 43.751 volts. Okay, so in 3 significant digits, it should be 43.8 volts. Because I am, take a look at this 7, and 5 is the one significant number right next to the 7, so I have to increase this by 1. So you see that you have to put as many decimal places as possible so that you can have a precise rounding at the end here, right? So if you miss certain decimal point here, it may turn into a 4, and then you cannot have 43.8. So this is in 3 significant digits. So we are going to keep as many decimal places as possible to provide a precise answer in terms of significant figures. Alright. Okay, so let's continue with the next example. Okay, for my next example, okay, I am going to ask everyone here to take a look at this. Determine the rate of change of the voltage across a resistor at a time t equal to 5.5 seconds, given this I and R, the two equations. So let me pause a few seconds. I want to put a reminder here for everyone. Okay, so a reminder. Okay, we need to be mindful of significant figure. Right? So significant digits, correct use of calculator. Okay, so this is the two reminder that I would like to remind everyone. The rest of them, I think I already remind everyone in previous example. And make sure you know how to work with your calculator, raise a number to certain negative exponent, and that exponent is a fraction. And I think there's videos that I posted in Blackboard for everyone to review the significant digits. Okay, and then make sure that we need to be precise. Figure or digit is the same things. Okay, and how do we keep our answer, final answer, as precise as possible? That means you have to keep as many decimal places as possible in our calculation. All right. Okay. So I hope that I cover everything. Okay, so I keep repeating myself regarding this because I know that when it comes to tests and quizzes, you may want to remind yourself of these. Okay, so this question doesn't say that I have to round to 3 significant digits. So uh, why do I need to do that? Because all of these numbers and the coefficients for this terms, they are presented as 3 significant digits. Okay, now you see in example number 4, I have everything presented as 3 significant digits as well. Instead of putting 8, I put 8.00. Instead of putting 0.03, I put 0.0300 because this number represents 3 significant digits and they all present as 3 significant digits. So our answer at the end should be the same. Okay, so the same significant digit, that's what I should say. Okay, so now this example asking me to determine the rate of change of the voltage across a resistor. And if you go back to the formulas that I gave you, I don't have any the rate of change in the voltage across a resistor, right? So then voltage across a resistor, so if you go up to the formulas that given to us at the very beginning here, we have a voltage here, V, but then we are looking for the instantaneous voltage and we have an inductor present in our circuit. This one is just the formulas for the power. So then how do we work with this example number 4? Okay, so example number 4 requires us to understand what it means by the rate of change. Okay, so let me ask you this question. How do you measure the rate? What do you base on in order to measure the rate? Do you have to base on time? Okay, so to talk about the rate, we are talking about something related to time. Okay, so if something related to time, it means that you are going to differentiate the voltage with respect to time. So rate of change is differentiation of certain value with respect to time. Okay, so in this case, I have it across a resistor at the time t equal to 5.5 seconds, given I equal to this and R equal to this equation, and they both represented in terms of time. So what I will do here is I know that there's Ohm's law. Ohm's law is V equal to I times R. And I mentioned this in previous reminder. Okay, so I kind of remind everyone on this page. Yeah, so this page I have voltage equal to current times the resistor. So that means we are talking about the current growing through this resistor. Okay, and we multiply that two value will give us the voltage measure across this resistor. And example number 4 indicate the exact same. It said that determine the rate of change of the voltage across a resistor. So what I will do is I will write that Ohm's law down. Okay, so Ohm's law is quite famous, right? So we cannot avoid working with any electrical electronics or any circuits without knowing the Ohm's law. All right, so what I will do is I'm going to ask you to multiply these two together, because I is given to me as this and R is given to me as this. So I can go ahead, and nothing wrong with writing it as AT plus 0.03, and at the same time I will convert this to the exponent as well. Okay, whatever term that I have as a radical, I am going to convert that into exponent. Alright, okay, so then I will have AT times 0.03 t to the exponent a half, 18 times 18t subtract 0.3 times t raised to exponent 1/3. And you see why writing my calculation down, I don't need to put 3 significant figures in any of this number, because these significant figures reminding me that I need to have my final answer as significant, 3 significant digits. And in writing that, I don't need to write all of that down, but I need to be mindful of my decimal places, right? Okay, so nothing wrong with I times R. I is given in terms of t, and then this given in terms of t, I'm going to multiply this together to find my V. Okay, to find V, because before I can find the rate of change of voltage, I need to know the voltage first. Okay, so at this point, you probably asked me this question: can you do this at the same times? Can you immediately find the dV over dt? Because I want to remind everyone is the rate of change, okay, of the voltage across a resistor, representing derivative of V as a function of time. Because what you want to concentrate is the rate of change of the voltage. In order to measure the rate, it has to be related to time. So you may want to immediately after this step, you may want to take derivative of V as a function of time. Then you have to differentiate this as a product rule. Okay, so then you differentiate this as a product rule because you have that multiplied by that, but I am not going to differentiate it yet. I'm going to simplify my process by expand, or I will distribute the terms. Okay, so I expand this out. Then after I have all the term on its own, I will differentiate V. Okay, so but if you take derivative of V as a function of time and you apply the product rule, then it should be the same. Okay, however, I don't recommend that, because right here you have t to exponent a half, t to exponent 1/3, and then the product rule is a lot more complicated. So if we can just expand, and then we find the V, Okay, find the v first, and then we will differentiate each term individually. Okay, so I make a note here that I will expand this. I will say here expand, then find derivative of v as a function of time. Will make it easier. Okay, easier than using a product rule. Okay, so expand, then simplify, so it's a lot easier than you differentiate and then you have to apply the product rule. So when I multiply this out, I should have the answer as 80 times 18t. I will have 144 t squared. Okay, and the next step is 0.03 times 18. I should have minus 2.4. T to the exponent a half plus 1 will give me t to the exponent. I think the next step I do is I take 80, I multiply by 0.3 t to the exponent here. So I better have my arrow. Okay, so I will do one arrow at a time. Okay, excuse me. I better follow the arrow. Okay. All right. So first of all, I do this. Okay, so I have that values. Okay, so the next step, what I do is I actually take 80, I multiply by 0.3 to the exponent 1/3. Okay, so my next step is this. All right, so then I will write 2.4 t raised to exponent 1 4/3, because I have 1 plus 1/3, so I have 4/3. So my next step is I am having this value, okay, multiplies with each other. So I should have plus 0.54t, and a half plus 1 will give me 3/2. And my very last term, I take this multiply by that. I should have a positive value or a negative value. It is a negative value because it's the positive here multiplied by that negative, and I should have 0.009 and t, and I take a half plus 1/3. I have t to exponent 5/6. Okay, so just make sure that we are remind ourselves of this formula. If we have two power with the same base and we multiply them with each other, we are going to add the two exponents. Okay, let me write it again. M plus n. Alright, so a reminder here. So why do I have, because this is t to exponent 1 times t to exponent 1, and this is the one with the t to the exponent a half plus I think to the 1 times t to the 1/3. Okay, so this here I should have t squared. This here I should have t to the 4/3. Okay, and then this one I am having this as a half plus 1 t to the a half plus t to the 1. Okay, I just want to go over step by step so everyone knows what the exponent coming from. And the exponent is so important, all right, because if we get the wrong exponent from here, our entire answer will be incorrect. So this one I should have t to the a half, okay, t to the a half times t to the 1/3. So this one I should have t to the exponent 5/6. And let's write that formulas down here. AM times AN is AM plus N. Alright, okay. So this is the reminder for everyone. So after I have all of this, and I see that I cannot combine any of these terms, they all have different, they are all unlike different terms here. They don't have the variable with the same exponent. So now I am going to start differentiating. Okay, before I differentiate, I double check one more time. Square, this is 4/3. This is 2 to exponent 3/2, and that, and that. Okay. So now, rate of change for this voltage is in fact dV over dt. So I will write derivative of V as a function of time will be equal to, so there's a lot of writing here, everyone, okay? So it's 288 times t, right? So the t square, you reduce that exponent by 1. So then I just have t left, and I take 4/3 times 2.4. So this is t to the exponent 1/3 plus 0.54 multiplied by 3/2. And I take 1 from the exponent, so this should be a half. And I have subtract 0.009 times 5/6. Now the t will become -1/6 because I'm differentiating and I take 1 away from the exponent. Okay, so just remind everyone here. Okay, so anyway, I only have 3 minutes left. So I am going to make sure that I give you all the answer. So dV over dt, I am going to substitute the values in, okay, evaluate at t equal to 5.5 seconds. So I have 288 times 5.5 plus 2.4 times 4/3 times, so let me skip this step because everyone knows that I substitute t equal to 5.5. So then I am going to ask everyone to make sure that you get this number. Okay, so this number with t equal to 5.5, I will get this number, and subtract with this number here, I should get is 5.64856, and this number, add that with 1.89962, and this number I subtract 0.005645045. In the end, the final answer should be this 245415. And as engineering notation, okay, I at t equal to 5.5 seconds, I should have 1.58 kilovolts per second, okay, in 3 significant digits. And in engineering notation as well. Alright, okay, so hopefully it's pretty clear of what we have to do. And don't forget the rate of change is to differentiate voltage as a function of time. Alright, thank you everyone. I am just on time.